Okay. All right, let's see how we're doing. Let me just put up the participants list. So we have only a couple people here today. So I invite you to, turn on your camera or unmute and ask questions directly so that we can also have a chat. I mean, this is a small tutorial, right? So it's actually a lot easier to do it that way. Okay, so I hope you have done the assessment that's online. It's not worth anything in particular. It's just to make sure that you're clear about the methods for doing the e-exam next Monday. So you need to come in a little early for that. Thanks, Junjie, for putting it on. Um, and then be able to go through all of the work. So basically what you need to do is go into coursemology, take the assessment there, okay? And then after that, hopefully everything will run according to your proctor. So your proctor will tell you when to start the exam, when to stop it. And it's very important to listen to their instructions because they'll have the exact time when your section in your proctoring area started the exam. Okay, so that's all good. So yeah, again, I invite you, besides just asking me on the poll, is you can, because there's only a few of you, you guys can ask me directly. But let's go to the questions first, okay? So I think the one about candidate elimination came up a little earlier. So let me try to address that one first. Yeah, I don't know why it does this. It's supposed to let you, yeah, click on it so that you can actually see the whole thing, but never mind. Okay, so is it true for candidate elimination, there's always only going to be one specific hypothesis? So maybe whoever wrote that question could elaborate, but basically, yes, that's always true. In candidate elimination, for the specific hypothesis, there's always going to be just one. If there's a, you can think about a counter example about how that might work. If there's more than one, what would that look like? Right, because of the way the conjunctive algorithm works, when we have positive examples and we want to shrink uh, um, the space of the most specific one, right? We want to make it more general. It's going to have to encompass that particular um, input, right? And then that means the border for the most specific hypothesis would be enlarged, right? But there's only one direction it can be enlarged. It's to fold that particular um, positive example into the plausible hypothesis space. Okay, so if you're not clear about that, again, I invite you to unmute and chat with me. Again, there's not that many of us, so we can definitely discuss this. Okay, because it's really basically a tutorial. Okay, but definitely you've seen the case where for the general hypothesis, right? There are many ways that we can shrink that, right? It could be that the negative instance is negative because of a particular attribute being positive, right? So sorry, being negative. So turned on and being a negative example. So that's why the negative space gets changed into several different hypotheses. So then it basically forms a lattice, right? You have these several general hypotheses, one specific one, and then you jump them together, right? Anything in between would be the space, the version space that we would have, right? So I can also go over that in the slides again if you'd like. So just put some indication, either unmute or turn on your camera and talk so that I can know whether I've addressed this well enough for you. Okay, I'm gonna assume that's okay because it's really hard for me to interact with you when I don't have any indication, but we'll try our best. Okay, so the other question is, I'll just do the next one here. It's supposed to, yeah, I still can't get this thing to work, behave properly so that it will let me mark things as done. Okay, so assume H is fixed and we increase the complexity of F. Why does it have a higher tendency to overfit? Okay, that is a great question. And it comes back to, again, this problem of bias variance. And I think, as you've heard from some of our external guest lecturers, who we spent some time to record, it's one of the most important things that we want you to get out of machine learning. Okay, so it's really worthwhile to spend some time on that. So let's go to the slides. I'm just going to leave that over here. I think you guys can all see. If you can't yell or find some way to tell me that it's not working, okay, because it's hard to get any feedback. Let's see. Let's go to. All right, so let's just go to this slide here in particular, because I think this is the one that many of you are concerned about. Okay, so let me see what I can annotate with the other screen here. Yeah, now I'm back on a Mac device, and Macs don't have touch screens, but hopefully it's more stable. Okay, so the question is about this particular screen again. Okay, let me just double check what you wrote. Okay, so assume H is fixed. So we have a fixed hypothesis space, okay, and we increase the complexity of F. Why does it have a higher tendency to overfit? Okay, so this particular question has to do just on the right-hand side of this diagram, right? Just the right-hand side, because if you remember, if you remember this part of the lecture, basically we were talking about having a fixed F. So we have our fixed H. Our H is not changed, okay? And here we are looking at the change of the number of data points, right? But also the change in the target complexity. So this is when we increase our underlying target function to be more complex. So by the numbers that you can see, going from 0 to 100, that means the the powers of X that we are looking at. So we might have just a single variable, x1, for example, okay? But it might come in a polynomial format, right? Where you have powers of X, like, for example, x1, X to the first power plus X to the second plus X to the third plus X to the fourth, right? All the way to X to the 100. Okay, and when we've set different coefficients on top of that, right? So if I have theta 1, theta 2, etc., that's what we're talking about here, right? So up to theta 100. So just to make clear, we're not talking about, at this point, having multiple features, right, that are in X. We're talking about having a single feature X and having multiple powers of it. So the target complexity could still be having a polynomial function, but it's only in one dimension. It's only of one feature, right? One dimension. Okay, so these would definitely be different features then, right? So even though we have one x1, sorry, I'm annotating the wrong screen. Even if we have only one x1, it can be to different powers, and then you would have different weights for each of the coefficients. Okay, so here we're looking at this one variable and we have a different target complexity. And when we increase the target complexity, basically the underlying target function gets more wiggly, right? So if you remember the sine curve that we drew before, let's see whether we can get an extra slide for that. Okay, let's go to here. Okay, so I'm just going to delete my annotation. Okay, and so if we have wrong screen again, a function that has some points, right? These are the points sampled from our data set. Let me get rid of this so it's a little nicer. Okay, then a higher order polynomial would actually get these sample points perhaps with a much more wiggly curve, right? Something like that. Whereas a lower order polynomial would get something probably a bit more gradual, okay? Something like that. Okay, I would have to actually go through that point right down there. Okay, something like that. Okay, so this means that when we increase our target function, when we sample the data set through, the data set that we get for training, it's going to have more variance. And that variance is what's causing this amount of stochastic noise, okay? Not stochastic noise. Deterministic noise is causing the variance, right? So variance happens in two different aspects, okay? We made hopefully that clear, okay? Is when the H that you get, okay, the H that you get, and then the target function that you get are not well matched. That's one source, okay? So in your question, you were asking about the target complexity getting more complex. Why does it overfit? Okay, and it's because that again, the target function gets more varied. So when we sample the data, it has more variance. And then even if we fix a particular hypothesis set, it will get worse. Okay, so that's why on this particular part here, you can see as we generally go from bottom to top, okay, the color gets more and more red, right? Indicating that H10 overfits more than H0, okay, H2. So even using a even lower powered H will help in the case of this, all right? Okay, the other point that we were talking about is actually also on this slide, which is about the case where we have insufficient data points. So that is on the x-axis here, right? So if we look at the x-axis, right, you can see as we go from left on this axis to right, we get more data points. Then the higher order classifier starts to have enough power to fit the data well, okay? And that's when you can see in this blue region on the right side of the graph, an H10 classifier is going to work better than an H2 classifier because again, this is the overfit measure, right? This is how we're defining the fit, okay, based on the difference between the test score, right? The test error on H10 versus H2, okay? So does that clear up what's going on this graph on the right? Okay, if you follow that, you can give me a yes. If you're still not sure and you want me to explain a bit more, I'll be happy to do so. This is a rather complicated graph on the right compared to the one on the left. I did go through it on Monday, but if you're new here, that's no problem. I can also go through why there's these different regions down here, why that looks like the way it is. Okay, so if you have any feedback for me, whether that explanation is clear, you can just go to your participants point and put a yes or no. So thank you, Ziming, for doing that. Thank you, Hans, for doing that. If there's anyone else that would like some more detail on this slide, I can go through that as well. Okay, so it's again very important that you understand bias and variance. There's basically, again, two different parts that you should remember about deterministic noise, okay? And it's basically coming back to those two parts, okay? One is that there's a mismatch between our QF and our H, okay? And as QF goes up and this gap gets wider and wider, it makes more sense to use a less powerful classifier to do the fitting, right? Because QF is going to be varying more wildly, okay? And the second part is about M. So a lot of things happen to work well only when we're provisioned with enough quality data resources. So remember when we are talking about data resources, we weren't just talking about number of points, but we're also talking about this part, right? Which is the quality of the data. If you have a lot of sample points, but you've gotten a lot of stochastic noise while measuring, that's probably not as good as having a few points that are measured well. Okay, so both of these factors factor into this idea of what we call M, right? So even though M is the number of points, we still have to consider how noisy they are. So I should actually write this probably as M and as sigma squared, right? The amount of noise that's there. Okay. So at least two of you got it. The rest of you, Kimberly, Paul, John, Jie, Shinsun, if you guys are not clear, let me know some way so that this office hours can be helpful to you. Okay, I'm going to assume for the sake of not having a lot of participation, thank you, Paul, for indicating, okay, that you're all good with that. All right, so we'll go to the next question then. Yeah, okay. So we answered this question. The next question is complexity affects the bias variance trade-off, but does noise affect the bias variance trade-off? Okay, that's a really good question. I think the answer is, if you're talking about stochastic noise, the answer is no. It affects everything equally, right? It will increase the variance, obviously, because you have more noise, your data point sample will be moving around more, okay? It won't affect the bias because the bias is, again, a function of the hypothesis space you choose. It will affect the variance a little bit, and by virtue of affecting the variance, it does, in some ways, affect the bias variance trade-off, right? Because you can think of it this way. Let me see, again, I'm gonna move to the other slide. So we have a little bit of a whiteboard here. Okay, let me move it away. And get rid of this ribbon. Can I get rid of this thing here? Yeah, okay. Is that we can think of basically having some error, right? And part of it is going to be due to bias problems, right? Which is our deterministic noise. And then part of it, where did this go? Yeah, okay. Part of it is going to be noise, right? This is our stochastic noise. And then if you just don't think about this part, right? The stochastic noise, we can further decompose this, right? This part we can think about, again, having the bias variance trade-off, right? So if we're going to delete that, okay, can we get rid of all these things here? Okay, then basically what we are looking at, as we saw in one of the post lectures, where's my pen? Okay, that we have two parts, right? One part due to bias, which is just our selection of our H, which H are we using? Okay, and our variance, right? And our variance is dictated by the particular sample data set D that we're drawing, okay? Which D, okay? So I should have swapped that around, but I hope you understand what I'm talking about, okay? So there's these 3 points that we, these 3 segments that are always responsible for this, okay? So it depends on where you mean by noise. If you're talking about stochastic noise, by default, it doesn't change the part between bias and variance, right, directly. But of course, the stochastic noise will be responsible for making your data set D worse, right? Because there's more variation and you can't control that. The best thing we know about Gaussian noise or random noise, right, is that in the limit, when we have M go from 1 to infinity, this gets washed out, right? Because, the Gaussian noise will average out, just like you saw for stochastic gradient descent, and then you'll get a clean signal, right? You'll get nothing but the signal back because all the perturbations happening to individual data points will cancel themselves out when we have large M. This is why it's always really good to have more data, even when there's noise, because we can cancel that out. But certainly stochastic noise does still have an effect, right? So we saw that on the graph in the slides as well. Let me see whether I can go back to that slide. Okay. Yeah, on here, let me just try to shrink this out a bit. Okay, so let me undecorate my slide here, right? So on the left-hand side, we saw this, right? When we have stochastic noise going up, having more and more noise levels, so the amount of noise is going up by, our sigma squared is going up by unit values here, and we get worse fits, right? But these are all canceled out when we have enough data points, right? When we have enough data points, then again, the noise level will cancel itself, and then a higher level classifier like our H10 will tend to work better than our H2. Okay, so let's see. So I hope that answers this. It's a really nice question that you asked. Thank you for that. So if you're clear about that, that's great. Again, if you're not clear about that, please do something so that I can know that the answer isn't good enough. Then I'll try to elaborate. Okay. All right. So let's go through, don't need to apologize, okay? It's a lot of complicated math. I know our CS students, I'm one of them. I don't really like math so much. So I feel your pain, but it's important to get the basics right. And some of the math is really, really cool. Unfortunately, we don't have a lot of time to go over it. So if you're a math geek, this class can be taught much better to accommodate your interests. And some of our TAs are much better at math than I am, to be honest, okay? But we take sort of a middling approach so that everything goes well. Okay, so I'm ranting, sorry. So let me go on and get the slides for regularization. Okay, let me make it clear. Regularization is not on your exam. Okay, I know a lot of people are like, okay, well, you know, Min covered regularization, and I saw past papers on regularization and validation. That will be tested, but not this test. It will be on your exam too in week 13. So if you don't really understand it now, it's okay. You can wait until week 13 to understand it. But of course, by then, you'll be busy with too many, 10 other projects, 10 other exams. So it's good to get it down now. So let's go over it, okay? I just want to make that clear, in case you were like, oh, panic, I haven't studied that. Okay, let's go to PowerPoint and pull up that slide. Nope, I'm not saving that. Okay, yep. Good. All right. All right. So when we're solving for regularization, let me get this out of the way. Okay. When we're solving regularization, we are thinking of just having this part, okay? So we have, again, contours, okay? This is actually, yeah, our sigmas, sorry, not sigmas, our thetas, okay? So here we have a function, for example, that is of H1, okay? So it's an H1 classifier. It's basically got a slope, right? An X plus an intercept, and a bias term, right? Our bias, okay? And I've got two parameters, our theta 1 and theta 0. Okay, let me move that over here, okay? So I'm trying to determine those two sets of values, right? This one and this one. And I can fiddle with this as much as I want, okay? In order to minimize my loss. And just pretend for a second that I've done that for all possible sets of values that I'm showing from here to here and from here to here, okay? So the heat map is basically illustrating the loss function, okay? And so what I want to do with gradient descent is keep on stepping from an initial vector. Maybe my initial vector is all zeros, okay? So maybe we start here. So I set this equals to 0. I have no intercepts. That's why it's at the origin, okay? And I want to move from here, right? I want to find something that's better. I find the derivative, the gradient, if you think of it in the vector form, a gradient of these two things through partial derivatives, and I want to take a step in the right direction, okay? So with the heat map, basically what we're showing you is where the loss function gets minimized, right? So higher levels of red mean it's less and less loss, so we are trying to step a little bit towards the middle, sorry, towards the middle of this region. That's where we want to go, okay? This is the best solution that we can find for our regularization, our actual solution for our linear regression, okay? So that's what we're trying to do, okay? But we have this additional constraint, right? The additional constraint is this, okay, that we have a budget, which we talked about earlier, right, in the previous slide. So if you're not sure about what the budget for regularization is, again, let me know. we're going to cover it a little bit more. Okay, it just basically says when I take the norm of the weights, okay, the square of the weights, they cannot exceed a certain amount, right? And that budget is called C. Okay, everyone with me so far? Okay, if not, again, just let me know on the participants list. Slow down, go faster. Those are also options in Zoom, so you can tell me that. Okay, so what's going to happen is our constraints, right, dictate basically if we're using this idea of squared weight, sum of squared weights, which is what this formula stands for, the one that I circled, right? It's going to allow us to define a hypersphere around the origin. Okay, so in this case, we only have two parameters, theta 0 and theta 1, so it's a circle, right? So it's easier in this case, right? So what we're going to do is define, the budget will define a circle, okay? So if you think about this, the solution that I could propose after doing all the training can be anything inside of this disk, okay? Let's pretend, for example, I have a small budget, okay? Okay, so I'm allowed to do anything. I'm allowed to set my parameters, theta 1 and theta 0, to anything inside of this disk. Okay, that's all good, anything inside of that. Okay, now what I want to convince you about is when the solution of linear regression, or the best solution for the loss, okay, is not in that disk, okay, it will be a point on the outside, around the perimeter of the circle, that is the optimum value. That's the best that we can get, okay? So you can see over here, it's going to be something like this point over here, right? Because that looks like it's the closest that's going to be dark red, okay? Now, when we think about our heat map, right? Our heat map is doing the opposite in some ways. We're coloring all of the space according to our loss, right? Our loss is this thing over here, okay? Which is basically a function of whatever points that I choose, weights that I choose, and how well they're going to match my target function, all right? And what I'm going to do is just draw contours. You can think of it as a contour map, right? And so all of these ovals that I could draw, let me draw a couple other ones. Come on. Okay, I can't draw so nicely with the pencil. Okay, but you get the idea, right? So things of this sort, all of these contours have the same cost. They have the same training error. And basically that if I step around the contour of these are all the same, okay? All right, so this sort of encapsulates all that. So I got rid of the heat map on this slide, right? And so we're gonna go through the observations, right? The optimal set of theta, right, our weights, is trying to get us close to our linear regression or whatever algorithm we're using, okay? The correct solution, okay, that we can do unconstrained. That means you give me unlimited amount of budget for my weights, okay? I solve this as best as I can, and that's where it is, okay? So I will definitely be on the surface where I can get this, okay? Now, when I think about the optimal set that I have on the regularization, it, as I said, is going to have to lie on the surface of this circle, okay? That's what I'm indicating here, right? Because anything that's inside of here is going to have worse values of loss, unless this particular point, okay, happens to be within the budget. So you can think about that. If I had a very large C, okay, very large C, something like this, okay, then I have no problem. The solution for my linear regression is inside of the budget that I was, that I was provisioned, so I can choose that point, right? But normally we apply regularization so that we don't have the full set of hypotheses. We're restricting from this huge space, right? This entire space over here. We're saying all of these things out here are not so likely. Let me just constrain the weights to things in this circle, right? And we know the reason why we want to do that, because having lower weights makes our polynomial function wave less, right? So our variance is going to be much less when we get samples that somehow are not going to help us to get a good fit for our function, okay? So that's what we mean by that. So the surface here, okay, of C is going to be perpendicular to our gradient of our loss function, right? So you can see that over here, okay? So in this point over here, you can see that the gradient of our loss is this blue arrow is pointing this way, right? Which means that if I want to lower my loss, I have to step in this direction. That is the best direction to step if I was having this set of parameters, right? That's what gradient descent would tell me to do, okay? Because again, if we look at this constant loss, okay, the best place to step is towards the opposite of the gradient, okay? So what we're going to do is say, well, I have this, I have to stay on my circle, right? Because that's the budget. I'm going to keep moving my solution, okay? And keep on stepping in a direction that's going to lower the loss, right? Because if I moved in the opposite direction, let's say I moved in the green direction here, okay? That is going towards the gradient, right? So it's not the negative gradient, so I'm increasing the loss this way, okay? So that's no good. I don't want to do that. I want to step in the opposite direction, right? And so the best place that I can pick where it's a stationary point is gotta be here, right? Because that's where I can't go any further, right? I'm at the point where if I go to the left or I go to the right, I'm going to increase my loss, right? Because the gradient is pointing that way. The negative gradient points directly this way, which tells me I'm sort of stuck, okay? So that's what we're saying with these 2 points here, okay? So that's the idea that we're trying to do. Okay, so we can get to this idea where our delta train, our gradient of our training loss is of a proportion of, in proportion to the norm of the regularization solution, okay? So that's just over here, right? So we know that we have a vector pointing in this direction, so we can just choose that, okay? In such ways as there's a constant of proportionality, okay? So we're just gonna choose something of this sort, okay? So we choose this just for the math to work out. It really doesn't matter, okay? The whole point is that we want to define that point, the regularization, okay? Everyone okay with this so far? Okay, thanks, Hans. Anyone else? Okay, the whole point here is that we want you to understand that, you know, when we have a certain budget, okay, as defined by our red circle, okay, we are always going to choose to take a point, okay, a setting of our thetas that is going to be optimal to minimize the cost, okay? And by minimizing the cost, it has this nice property where the gradient is going in the opposite direction of the normal to the circle, right? So our normal is in red, okay? It must be exactly opposite direction of the constant loss of the, on the training data, okay? So hopefully pictorially you can understand that I'm a little worried you guys are lost. So if you are, let me know, okay? That's important. Okay, so what does this come down to? All right, we saw when we were doing gradient descent, we can do optimize this directly. Okay, sorry. Okay, we just choose a bunch of parameters. I get a gradient and I step in the appropriate direction, and then I do this all over again n times. Or I can use, sorry, I keep on annotating the wrong screen. The one-step solution, which is our normal equation, which uses the pseudo inverse, right? That requires a matrix inversion. Okay, so now on the right-hand side of the screen, okay, on the right hand side of the screen, I'm trying to do the same, but now with a particular constraint, right? I said, I want to set a budget. I'm not allowed to go over that, okay? So instead of using this hard constraint, I'm going to change it into an implicit constraint, okay? So the implicit constraint is just that, I'm going to, again, minimize the training error, which I had in the original case, but I'm also going to minimize, okay, a term that allows me to have this solid constraint, okay? So that's all that I want to do, okay? So I put this term, right, which is, again, a translation of this, okay? But for all m points, okay? Why do we do that? Because I want to be able to factor it out later, right? Because when I talk about my training costs, right, we saw that the training cost is a point-wise error cost that we are averaging, right? So that's why we also want to do this part where we are thinking about averaging over all endpoints. So I can factor this 1 over m out over here, okay? So when I do this, that's why the m is here. Then I just get this form for everything else, right? Because it's basically averaging over all of the point-wise losses for the individual points as well as the regularization cost, okay? So all's good there so far, right? Okay, so basically all we did was we translated, okay, our C into another parameter, lambda, okay? So it's just a translation in proportionality so that we can get our m factor to move out, okay? So whether you use C or lambda, it doesn't matter. C looks nicer geometrically on our slides, right? Because when you have C, then you can draw this nice circle. When you have lambda, that C is the circle is going to change size depending on how many points you have. Okay, so it doesn't look so nice. Okay, so that's why we are using it C in the earlier one. Okay, all right. So then we're going to do the same thing as you saw in the other lecture where we're deriving the normal equation, right? So we are going to say, well, if I want to minimize, that's very easy, right? We minimize things by using calculus, right? We take the first derivative, set it equal to 0, and then we're done, okay? So in the vector format, it's very simple, right? You can just say, I have a whole bunch of partial derivatives. I can do them all simultaneously with the same type of math, okay? And I'm going to set everything equal to 0 here, okay? So I have a vector of zeros, okay? I'm going to set all of these through that, right? I take, basically I take the derivative of this with respect to theta, right? Because we're changing theta, okay? So I take the partial derivative, right, of this thing up here with respect to that, with respect to theta, and I am going to end up with this equation down here. Okay, let me clean up the slide again. Okay, so I've got thetas in a couple different positions, right? So I have the theta um, over here, and over here, okay? And those are results in the terms that you see below, okay? That you get at the end. And after some manipulation, I'm going to end up with a format very, very, very similar to what you saw on our linear regression, right? These are almost identical. The only difference is that we have an extra parameter of this gamma, sorry, our lambda. I'm getting my constants mixed up, okay? The lambda happens to be, of course, not with a single scalar constant, but has to be done over the entire vector space, right? Because we're dealing with vectors here. So we're going to have to take that lambda and multiply it against the identity matrix, right? So that's why there's this I here, okay? So once we have that, basically we just have this extra constant that we're using that needs to be folded into the inverse operation, okay? So we can solve augmented error and have regularization in the same amount of work that we would normally choose to solve linear regression. So that's the beauty of the math here, right? That you just add a constant value, this lambda, and then you're done. You can do the same type of optimization. You can use all of the same work to get the final figure, okay? So this is to solve it if you want to use one-step learning or the normal equation. This is the normal equation for regularization, okay? That allows us to do that, okay? But again, you don't have to do it this way. We can also try to do it through gradient descent. When we do it through gradient descent, it's no different, okay? We're still trying to do it like this, okay? Minimize this, okay? It's just that we take the gradient, which we've done, okay? We take the derivative and we just take steps one at a time. We're not gonna actually solve this directly using the inverse, right? Because this particular bad boy over here is the one that takes up the most time, right? The inverse. So if you have a lot of data points, doing an inverse of something m times m is going to be horrible. Don't do that, right? So we're going to use stochastic gradient descent or mini batch gradient descent, and we'll solve the problem in that direction. Okay. Okay. All right. So I hope you understand what I meant by going through solving regularization. I think that was the last slide. Let me check whether that's the case. Yep. Okay. So I hope that was clear. Again, if you're not clear, please let me know because again, I really want this to be helpful to you because the lectures are probably more clear because they're recorded compared to an oral presentation now. Okay, so I'm just gonna hope that's fine. Again, tell me if not. When we discuss overfitting, do we always use the overfit measure comparing two models? No, we don't, okay? So that is just a visual method for helping you understand what we mean by overfitting. When people think of overfitting, they generally mean what we said on the slide earlier, okay? Which is that we fit the data more than is warranted, okay? So what does this mean? It means that when we fit the data in the training data, we fit it so well that it starts not to generalize for our test data, okay? So again, when we are actually doing the fitting of the data in the test training time, we have no idea, right? What is noise, what is signal? So we have no choice. We're gonna try our best when we optimize and lower our training costs. We're always gonna try to fit the data better, right? What we're doing with regularization and other techniques like cross-validation and validation is to put the brakes. You say, you know, maybe you are already fitting good enough. You know, if you studied and memorized patterns that, you know, if Min offers a question that has the number 5 in the midterm, the answer is always D, you are probably going to get it wrong. You're not generalizing enough. You fit the data too well, okay? So that is what we're doing, okay? So it just happens that in the case where we know where the target function is, right? We have this QF parameter, which is not in real life, right? This is just a simulated experiment where we have full control of a target function, which we can draw points from, and then we can provide it to a learner. The learner has no idea what QF is, what the actual polynomial function is. Then we can show how things overfit, right? So often we would just say things are overfitting without referring to another possibility, okay? So you can say two models, okay? We do that when we're talking about validation, right? So when we go to validation, we are actually using information about multiple models, right? We have the model that is on the real training data, which is basically the training data that we have. Okay, let me just draw it here. Where did I had an extra slide here, which I used before. Okay, well, let me just add another slide then. Okay, and I'll get rid of all these things. Okay, so again, in regularization, what we did was we took a data set and we cut off a part, right? And we called this validation. And in the that lecture, we said usually you take about maybe about 10 to 20% of your data and use that for validation. The rest we use for training, right? So this is our training data, okay? Our validation data is going to simulate the idea of test data, but it's test data that we actually have the labels for, so we can assess what is our J-val, right? So we're going to hope that, again, it approximates our J-test, okay? That's the idea. Okay, we also saw in the part where we're talking about the benefits of having a validation set is that the variance error trails off by 1 over square root of k, okay, where k is the number of points that we're using for our validation, right? So having a validation set is good. Having more data is helpful, but having a lot of data is not so helpful, okay, because again, it tails off our variance error in estimating J-test tails off with square root of k, okay? So let me get back to your actual question. Okay, so yes, so in validation, we actually do this comparison, right? We do look at two models, okay? Perhaps one with a particular model, another with a different classifier, or it could be the same classifier with different regularization amounts, okay? All of those are possible, okay? So you actually have two models, and now what we're doing when we optimize is we choose the set of hyperparameters with respect to how well the validation loss is doing, right? So we choose that, and we saw in the lecture, it leads to an optimistic bias, right? We'll get worse, sorry, we'll get a validation loss that generally is a bit lower than our actual test loss, because we are using this estimated loss, okay, on the validation data to approximate what we should be doing for our test data, okay? All right. So I hope that one is clear too. This is also a nice question that you guys asked, so I appreciate it. Okay. Anyone got questions that you're not sure about? Sorry, I missed your chat. Okay. So John asked, okay, in case of just H2 alone and an increasing complexity of F, why then would the variance increase lead to more overfitting? Okay, when you have H2 alone and increasing F, why would variance increase? Okay, so here, again, there is exactly what you said. There is going to be more loss due to bias, right? The bias error is increasing because the fit between your actual classifier, H2, and an increasingly complex QF, right, going from, let's say, H10 to H20 to H100 will get larger, okay? So yes, that is correct. Your bias error is going to increase, okay? But variance should not, okay? So your variance error still goes up, okay? Because with the data set, with the points that I can pick, okay, for a larger QF function, the variations of what I can get in those 2 points will go up, okay? So it will go up, so the variance error will still increase, okay? That is what you saw on the graph earlier. Let me see, I can pull it up. Okay, if you remember that one, oh, I'm looking at Chrome, sorry. I'm not paying attention. Bias noise, right? Yeah, this one, okay? So even if you're not looking at H10 and H2, okay, generally speaking, as we go higher and higher up in these curves, right, the propensity to overfit for a larger target function with more complexity will go up, okay? For any class, whether you use H10 or H2, just because the points that you get are going to vary more widely with a more complex target function, okay? It will get worse when you use a higher polynomial to approximate, because again, the higher order polynomial like H10, because it has more knobs, can fit those samples better than H2. But it's, again, because you only have a small number of points, okay, compared to the amount that's needed to approximate H10 very well, it's almost always better to use a lower powered classifier, okay? So I hope that answers your question. Again, if not, let me know. We will definitely want to help you. Okay, and I will say this, this lecture is very important for bias and variance, but as you'll see, when we get to neural networks and deep learning, and many of you are doing projects in this case, a lot of what we know from bias and variance and having to try to use fewer parameters, smaller weights, seems to go out the door, because as you're following news in ML, for example, you hear natural language models having billions of parameters, right? So there are basically these theta scalars for billions and billions of neurons in a neural network, okay? So how could that be? I mean, we're arguing in this case for a model that only has three parameters, right? H2, theta 2, theta 1, and theta 0. And already you're telling me that seems to work better than something with H10. The key here is that when you go to those models, it's about the, again, something like regularization, how they're able to determine the right set of values, even in the face of having lots of knobs, okay? So again, it's similar to regularization, okay? We won't go into it very much because, again, there's a graduate course on deep learning. There's much more to do about it, but we do want you to get some idea about what deep learning is about, because again, many employers are looking for deep learning skills, and of course, traditional machine learning is still very important. Okay, so it's a mix of both. Okay, and again, we made this decision hopefully to give you a good mix of what you need to get internships or to get your first course in machine learning. It is pretty different from other courses that you'll see in other places. Okay, from a traditional machine learning course or deep learning course, which sort of eschews all the math together, which we don't think is fair. Okay, let me get back to your question. Okay, may I know what is the bias weight theta 0 for? And is theta 0 the negative of the threshold? Okay, yes, that is exactly right. Our theta 0 is typically referred to a bias weight. And the reason why that is you can think that if I have any polynomial function, okay, let me see whether I can get a new slide here. Okay, let's just use this one. Okay, is that, well, if we're trying to learn some type of linear system, right, we're going to have some number of parameters like x, let's say to the 10th power plus x to the whatever, x to the 1, okay, plus a bias term, okay, 1, okay? And then I'm going to have thetas attached to those, okay? So I have theta 10, theta 9, theta 1, theta 0, okay? And if you think about this, if I set all of these to 0, okay? Okay, 0. If I try to plot this function, okay, this is actually a single function because I only have a function of one variable because I only have x here, right? So I can plot it. Okay, so let's say I have this, okay? And this particular function, if I set it all to zeros, would just be flat right there, right? Because it's going to simplify to y equals 0, right? There's nothing else, okay? So it's going through the origin, okay? But now, let's say I change my values, okay? Let's use green. Okay, I'm going to change these values to something else, okay? Something, but I'm going to leave my theta equals to 0, okay? So I can choose whatever number I want here, okay? So let's say A, B, and C, okay? So then I'm going to get a sum function, but it has to still go through the origin, right? Because there's no way that I can get it to move off of that. All of these other values depend on my value of x, right? So if x equals 0, right, then all of these terms are going to go away, right? They're all going to get set to 0. So these are all going to go bye-bye, right? And so what's the only thing that's going to happen is that whatever my theta weight 0 is, my theta 0 is going to be able to move my hypothesis off of the origin, right? That's the only way it can move. This is why we refer to it as a bias weight, okay? So the bias weight, as we'll see in neural networks later, we typically associate it with a constant 1, okay? That means despite whatever values of x that I have, my x10, my x9, my x1, okay, I'm just going to use a bias of observed bias of 0, sorry, of 1, okay, come on, circle, okay. And why do we use 1? It's similar to what we do in other things, like our SVM. We said we want to set the distance to 1. It's because it's an arbitrary number, right? Because if I set this to another number, it just means that I'm going to change my theta 0 in some way, okay? So right now, if I set theta 0 equals to 4, okay, that corresponds to translating that function to start at 4, right? So I just count 4 units on my x, and it's, whatever wobbly function that I have is going to go through x, y equals 4 when x is 0, right? If I choose a different number, okay, instead of using 1, let's say I choose 2, then all that means is I'm going to change this to 2, right? It's a vacuous scaling. I'm still going to end up with the function in the same place, but now, you know, I just have a different set of observations, okay? So this is what we mean by a bias term, okay? This is why, even though logically, we can say we have theta 10 through theta 0, okay? It's easier in some instances, especially in the SVM, and also when we're talking about discussing moving off of the origin, okay? So this translation here is basically due to our theta 0, okay? To decompose this into theta 0, theta 10 through theta 1 plus a bias term, which is our theta 0, right? So this is times our B, okay, and this is all of our x values, right? X whatever. All right, does that make sense? Okay, so that's why we do this part, right? That's why we call it a bias term, because it basically allows us to pull the hyperplane or whatever classifier we want not to sit on the origin, right? As soon as we set the bias weight equal to 0 or theta 0, we can't move it because everything else is dependent on a variable, right? So the only thing that doesn't depend on a variable will be the bias weight, our theta 0, that's multiplied, but usually by an artificial instance of 1, okay, that plus 1 that we saw just now that I wrote, okay? So just nice, it is almost 12 o'clock. So I just wanted to, again, make sure that you understand everything that's going to happen on Monday, because it's very scary for us to try to do this test, okay? But I just want to make sure that you're clear about that. So just bear with me a second while I take you through that. Okay, so I put this announcement. You should have gotten it. Make sure you get are receiving emails from our CS3244 account. Okay, this is all those purple header emails with the panda sitting there. Okay, if you haven't been receiving them or not paying attention to them, you will not have the materials for the exam. They will be sent later to you, hopefully by Saturday. Okay. We don't want them to go out too early, just in case somebody wants to try to crack the encryption or whatever. Okay, but we need to make sure that you have received it, so that your proctor will make sure that you have all 3 parts, and then they will be able to give you the decryption code orally as well as in Zoom chat when you actually take the test, okay? So in particular, make sure that you understand that it's the proctor who's giving you the test, okay? Even though I will be, you know, in my office here in SOC and monitoring things, I will not be actually proctoring your exam, okay? I will be overseeing everyone else that's proctoring, okay? So each proctor can set their timing for the test at different times, okay? We're all gonna try to start at the same time, but you can imagine some sessions may be a little slower than other if people have technical problems, okay? So whenever your proctor starts the exam, they will note down the time that they start the exam, and you will have to stop your exam at the time that they tell you to stop. The coursemology assessment, if you go to assessments here, later on, you'll see these that are open, okay? They will still be open for other sections to keep keying on their responses if they have not finished, okay? It doesn't mean that if your proctor calls time, you are still allowed to enter in things, right? Because you've already had your 25 minutes to do that section, okay? So we will be auditing and checking people who key in things after the time limit, okay? They will be penalized for cheating, okay? So just make sure you're very clear about that, okay? The other thing that I'll say is that, you know, basically, you need to be clear about how the clarifications, if any, will come up. You can raise your questions via Zoom chat to your proctor, and then your proctor will raise it to us centrally. We have a Slack group that we use for coordinating all of the TAs. We will use that to figure out what to do with your question, and then we will communicate it to everyone at the same time. The only way we can do that is by using Microsoft Teams. It reaches the entire cohort, okay? So when we do that, your proctor will also tell you, hopefully, if they're paying attention, what the clarification is on Zoom by chat as well as by audio, okay? So that you don't miss any clarifications, okay? We had problems in previous classes where people were busy doing their exam and didn't get notified about some change, okay? So that's why we are going to broadcast it in multiple ways, okay? So I think that's all. If you guys have any other questions, please let me know. Otherwise, I wish you a fair weekend, and I hope you're studying well for your other exams and midterms, and of course, doing well on your projects, okay? So we'll be getting in touch with you about project consultation right after our first exam, okay? So I think that's all I wanted to share with you. So yeah, if you got any other questions, great. Otherwise, I'll let you go. Okay, I don't hear anything, so I guess you guys are all good. You guys are just waiting for me to disappear, so I will disappear so that you can go. Okay, bye now.